Hello, welcome to another session of General Chemistry 2. For this session, we're going to cover the most essential learning competency, which refers to describing the following properties of liquids and explaining the effect of intermolecular forces on such properties, namely surface tension, viscosity, vapor pressure, boiling point, and molar heat of vaporization. For the unpacked learning objectives, number 1, for you as a student to describe the following properties of liquids: surface tension, viscosity, vapor pressure, boiling point, and molar heat of vaporization. And next, for you to be able to explain the effect of intermolecular forces on such properties of liquids. So as a review of our previous session on intermolecular forces, as you can remember, intermolecular forces are weaker than intramolecular forces. So when we refer to intermolecular forces, these are the forces between molecules. They are non-bonding forces. The following are the strengths of the intermolecular forces. Number 1, ion dipole. Next, hydrogen bonds. Next is dipole-dipole interaction. Next is ion-induced dipole, followed by dipole-induced dipole. And the most common intermolecular forces which exist between all molecules, what we call dispersion or London forces. Some of the references refer to it as van der Waals forces. So the first property of liquid that we're going to cover refers to surface tension. So the main point that you have to remember is that it is connected to the surface area, or in its um, most common definition, it is the phenomenon that occurs when the surface of a liquid is in contact with another phase. It can be a liquid as well. Liquid tends to acquire the least surface area possible. So as you can see on the picture, it's on the left side, we have the table containing some common liquids and their surface tension. For hydrogen, we have the surface tension of 2.4, helium 0.16, water 0.072 newtons per meter, ethanol is 22, sodium chloride is 114. On the right side is an example of the phenomenon happening in the morning. So yung pagpo-form ng hamog or dew is due to surface tension. And surface tension is also due to the intermolecular forces between the water molecules na nakadikit dun sa dahon. So let's now have the second property of liquid, which is viscosity. So just to differentiate it with surface tension is connected to the surface area, or when liquids tend to form the least surface area possible. Viscosity now refers to the fluid or the liquid's resistance to flow. So there's another table here which contains different measures of viscosity of different liquids. So one measurement for viscosity can be in Pascal seconds or millipascal seconds. So we have the common liquids like acetone, then we have water, ethanol, mercury, nitrobenzene. So as you go down the table here, for example, let's focus on the motor oil. So they have greater number or a greater value for viscosity, right? So for example, motor oil SAE10 at 20 degrees Celsius is having a viscosity of 0.065, which is greater than water. That's why Motor oil is the one being used for machines in order for you to maintain the integrity of the machine or the engine, because it has greater viscosity or it resists flow, right? That's why also you need to replenish brake fluids. Yung mga ginagamit na brake fluid sa sasakyan, kailangan mapalitan siya kasi kung hindi napapalitan yun, no, nawawalan yung or nababawasan yung viscosity. It can cause accidents if it isn't replaced. So the next property of liquid that we're going to cover is referring to vapor pressure. It is a measure of the tendency of a material to change its state to solid, liquid, to gas or vapor form when the temperature increases. So in short, it is the natural tendency of a liquid to evaporate when temperature increases, or when a solid directly uh, transforms into the vapor form. So it's connected to temperature. It also indicates the rate of evaporation of liquid. Also, it is closely related to the tendency of particles to escape from the liquid or solid state. So as you can see here on the picture, this is a pictorial representation of concepts of vapor pressure. So when there is a lid on the container, the gas phase molecules are trapped. They are a vapor. The vapor creates the pressure. So that's a representation of vapor pressure. That's why if you left the container open, so the tendency of the molecules is to escape the container and transform from liquid to gas or vapor form. So that's vapor pressure. So now let's go to the next property after vapor pressure. It's connected to vapor pressure also. It's now referring to boiling point. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure of the liquid's environment. At this temperature, the liquid is converted into a vapor or its gaseous form. The boiling point of different liquids is different for a given pressure. In 1982, the IUPAC, or the International Union of Pure and Applied Chemistry, defined the standard boiling point of a liquid as the temperature at which the liquid boils under a pressure of 1 bar. So as we can see on the picture at the right side, we have some common examples of liquids and also the alkanes in their molecular formula with their corresponding boiling point here. So as you can see, we have dodecane, or an alkane with at least 12 carbons. So its boiling point is 216.4. So most of the time, when referring to alkanes or those organic compounds with carbon, it usually is connected with the number of carbons. The boiling point is connected with the number of carbons. The higher the number of carbons, the greater the boiling point. But in the case of water, since it has a greater boiling point, let's now refer to the at 100 degrees Celsius at 1 bar. So that's the standard boiling point of water. As you can see on the left side, so at room temperature, the water doesn't boil because the atmospheric pressure is greater than the vapor pressure. But if you put it on a stove and heat the beaker with the water, there's after some time, the atmospheric pressure becomes equal to its vapor pressure. So yung orange arrow becomes equal with the blue arrow or the vapor pressure. That's the time when the liquid boils. So if you go to Mount Everest, which is the highest peak in the world, there is lower pressure or lower atmospheric pressure. So you need only lower amount of vapor pressure to attain its equivalent atmospheric pressure. So if ever you are boiling something in Mount Everest, so the time it takes to boil is lesser in a place at a higher point from the sea level. Kung saan mas mataas yung lugar, dun mas mabilis magpakulo ng tubig as compared to at sea level. So may epekto rin yun sa halimbawa sa pagluluto or sa pagpapakulo ng karne or kahit anong pagkain. So let's now go to the last property. It is called the molar heat of vaporization or the change in H VAP, or usually refers to the amount of energy absorbed by 1 mole of that substance as it is converted from a liquid to a gas. Since vaporization and condensation of a given substance are exact opposites, the numerical value of the change in VAP or the molecular heat of vaporization is just the same, but in opposite sign. In other words, the change in H or the change in enthalpy of vaporization is equal to the negative change in heat of condensation. So yung, for example, sa isang liquid may ang vaporization niya ay 10 kilojoules per mole. Then yung condensation niya is negative 10. So that's what we mean by vaporization and condensation being exact opposite processes. So let's now take the case of water. 1 mole of water at 100 degrees Celsius and at 1 atmospheric pressure is converted to 1 mole of vapor at 100 degrees Celsius. It takes about 40.7 kilojoules of heat absorption from the surroundings. So when 1 mole of vapor at 100 degrees Celsius condenses to liquid, 40.7 kilojoules of heat is then released into the surroundings. So that's how we can equate condensation and vaporization as exact opposite processes. So from liquid to gas form, the water takes about or absorbs 40.7 kilojoules per mole of energy. So it's an endothermic process. So it's absorbing energy in the form of heat. While in condensation, we are releasing energy. So it's in the opposite sign, negative 40.7 kilojoules per mole is released. So it's an exothermic process. So vaporization, endothermic process, absorbing energy. Exothermic process for condensation, it's releasing energy. So on the picture at the lower part of the slide, so it contains other substances and their heat of vaporization and heat of fusion. So for melting naman yun. So usually we will use for molar heat of vaporization, we will use the values for change in vaporization for problems solving processes. So let's have a sample problem involving heat of vaporization. The question is, what mass of methanol vapor condenses to a liquid as 20 kilojoules of heat are released? So let's take step 1. Let's list the unknowns and known quantities in the problem. We have the known quantities. We have the change in H. It is equal to 20.0 kilojoules, while for the change in H and condensation, it's negative 35.3 kilojoules per mole. So it's from the table earlier, but since it involves condensation, it would be in the negative value, so negative 35.3. For the molar mass, so the molecular formula of methanol is CH3OH. I mean CH3OH. So just add the atomic mass of carbon and 4 hydrogens plus 1 oxygen, that's equal to 32.05 gram per mole, or the molar mass of methanol. So for the unknown, we are looking for the amount of methanol condensed in grams. First, we need to remember that the kilojoule of heat released in the condensation is multiplied, or should be multiplied by the conversion factor of 1 mole over negative 35.3 kilojoules to find the moles of methanol condensed. So it's just a simple dimensional analysis. So we will start with the amount of heat release. So it's in the negative amount since it's released. So it's negative 20.0 kilojoules times the conversion factor of 1 mole of ethanol, which is releasing negative 35.3 kilojoules. So this is the molar heat of vaporization. So condensation, and the change in H condensation for methanol, times our molar mass, which we got earlier, 32.05 grams of methanol is in 1 mole of methanol. So using simple calculation, so kilojoules cancels, then the mole cancels, we are left with grams for the unit. So for the negative 20.0 kilojoules released in the atmosphere, so it is equivalent to about 18.2 grams of methanol. So thinking about the results, since condensation is an exothermic process, so it releases energy. So the value for the condensation is negative. So the enthalpy change, it's negative. So it's referring to the negative 20.0 kilojoules of heat released. So if you compare it to the original amount, slightly more than 1/2 mole of methanol is condensed. So if you can remember, if you refer to 18.2 grams and 32.05 grams, so it's slightly more than 1/2 mole of methanol, which was condensed into the atmosphere. So let's now have the next learning objective, which is to explain the effect of intermolecular forces on such properties of liquids. So in the case of surface tension, liquids with stronger IMFs tend to have higher surface tension than those with weaker intermolecular forces. For example, if you pour a very small amount of water on the table, it will tend to collect in one large drop. So if ever you have used the mercury thermometer, so usually when a thermometer breaks, the mercury droplets tend to form in the least surface area possible. So for viscosity, liquids with stronger IMFs tend to be more viscous. So oil is more viscous than water. So for letter C, for vapor pressure, substances with stronger intermolecular forces will have lower vapor pressure because fewer molecules will have enough kinetic energy to escape at a given temperature. While substances with higher vapor pressure are said to be volatile, that is why they easily evaporate. So when you compare alcohol and water, so alcohol has lower vapor pressure. I mean, so the opposite, alcohol has higher vapor pressure, so it tends to escape into the atmosphere at a faster rate than liquids. So next, for boiling point, the stronger the IMFs, the lower the vapor pressure of the substances and the higher the boiling point. For the molar heat of vaporization, the stronger the IMFs, the higher the energy needed to change the state of a substance from liquid to gas. Or in short, the greater the molar heat of vaporization. So for the last part of this session, please take time to answer activity 4 referring to the properties of liquids like surface tension, viscosity, vapor pressure, boiling point, and molar heat of vaporization. For number 1, why does it take longer to boil eggs in Baguio than in Chao? Number 2, cite situations at home where liquids tend to display the following characteristics: surface tension, viscosity, and vapor pressure. For number 3 is problem solving. How much heat is required to convert 50 grams of ethanol into its vapor or gaseous form? And also how much heat is released if the same amount of vaporized ethanol is available to return to its liquid form. So that's the end of our fourth session in Chemistry 2. Thank you and have a good day.